Hello, Matt.
Hello.
Seems like it's just you.
I hope someone else comes in.
Hey, be careful.
Do you have a 205 class this semester?
Yes.
Is it in person?
No,
On Zoom.
it's online.
Would you mind if Bowden or myself join that class to promote SPS?
Yeah.
Oh, sure.
Is that okay?
Yeah.
Just to say something?
Yeah. Just let me know what time you're coming and preferably in the early part.
Okay. Well, do you know what's the
12 o'clock to 12:50.
on Monday?
Monday, Wednesday, Friday. It's
Okay.
right before this class, 2 hours.
Okay,
before.
yeah, I'm free for that. And maybe
So, are you guys-
maybe this Friday?
Yeah, sounds good.
Friday. Do you have a class during that time?
That's fine.
I could try to sneak in the beginning, or it's an evening class, so.
So you can come to my office and, oh, where is it? Oh, would you guys like to do it online?
Yeah, just join the Zoom.
Yeah.
Yeah, because I have one that runs 212, and that's my house on Zoom for.
It's the same classroom as this. The same number, same password.
Okay.
So you can just try it.
Sometimes,
Yeah.
I'm used to.
Used to not by house, right? Doing it from here.
Yeah.
I inform someone, I guess. I should do it. I'll forget it. Yeah. Okay. So we have two. Does this disturb on the other side, by the way? The flickering, there's a light that flickers in this room. Do you guys just get to see that?
It's not that big a deal. We can see it.
Yeah, you guys, yeah, you should try to remember this then. Get it fixed. Or if you guys remember, if you just have to send an email to the physical plant, you guys know, just say that there's a tube light and this submit a work for that. But I will also do that. Okay, so there's a homework activity and there's a midterm. We talked about Ampere's law, and we discussed a very simple example. Here we want to do a little more of the simple geometries, and later, once I do the simple geometries, I'll come back to the situation where we do a little more elaborate problems with Ampere's law, but not too elaborate. Everything in principle, same at the same level as introductory physics. What we will start doing new is the vector potential, which we start deriving next week. So let's say we're still using Ampere's law. It stems out of one of the Maxwell's equation, and if we do not have any dynamics, that means it's statics. So one of the equations is L cross D is equal to mu naught times Q. Right? So that's a current density, which is also the current per unit area. If you were to integrate this equation about any area, break the area into small, tiny pieces of area, and area is a vector in principle. Its face has a direction perpendicular to the surface itself. It could be up or down if it is a flat surface, but typically it is part of a curved closed surface, then it is the outgoing surface. If it is flat, then you have to use the right-hand rule to specify the, it should be consistent with the right-hand rule. So there's a surface S, and that's the cross E. Use an integral on the surface on both sides. This becomes mu naught times same idea. But since current density is current per unit area, current density times area will be the current, but we don't have to add up all the currents, only those currents that's passing through this surface S. So this is mu naught times I enclosed, current that is enclosed within that area. And the left hand side, using Stokes' theorem, is dl divided with d. So there is a derivative here. Derivative contributes only at the boundary, and the boundary of the surface is a curve or a closed curve. From any surface, there is a closed curve, and this, if you want, you can also say this is the closed curve associated with this surface S, but the closed curve could be associated with many surfaces, so we don't really have to write that. Okay, so that's Ampere's law, and let's do a simple scenario here, and for that purpose, we want to ask for what geometry do we get uniform magnetic field? How can you generate uniform magnetic field? A parallel scenario in electric field, you can ask the same question: how can we generate a uniform electric field? Or for that matter, you can also ask, well, how do you generate uniform gravity? So how would you generate uniform gravity? Just suppose you want to, where would you get uniform gravity? If you want to see uniform gravity, where would you see uniform gravity? What kind of mass distribution will give you uniform gravity? Sphere. No, right? Mass distribution will go die off, right? Like Newtonian. If you go very far away, it will actually die off 1/r². How far you are from. So, what kind of mass distribution gives you uniform gravity? Let's begin with that.
Is it a point?
A point charge also is 1/r², right? So if you have a point mass, you have m/r², right? Same thing with, so this is a force, right? Infinite plane, yeah, that's correct. If you have a sphere of infinite radius, then that's equivalent to you being on the surface of the sphere, right? Surface of a sphere, you see mg. That's under the approximation that this is actually, we are very close to the sphere compared to the radius of the sphere. So infinite, a sphere of infinite radius, which is basically a flat plane. Then if you have a mass m, that's basically there is another surface, but this is actually mg, right? Where g is a constant. So talking about that, so this is just a digression. What kind of mass distribution actually gives you zero gravity? If you want to experience zero gravity, what's the simplest scenario? Be a little more precise. Yes, Sarah? Yeah, maybe you want to specify a little more? Because I just now said that if you have a sphere, right, and if you're here, right? So this is 1/r². But you still have a roughly. No, but then there will be constant. No, I just want to ask where. Oh, if you're at infinity, yeah, that is zero, but probably that's very. Maybe if I call it trivial, yes, trivial. It's like saying there is no gravity. But you have a mass next to you, but it is actually zero, not contributing. Zero gravity.
Small mass, right?
Small mass, again, that's a trivial solution in the sense that is equivalent to saying that mass is not there at all. Right? Where do you see zero gravity? Space, yeah, but space, is it really zero? 1/r², right? Because it is very weak. But then International Space Station, they always show you what is the, that's a good point. What is the acceleration due to, just estimate? Yeah. What do you expect will be the acceleration due to gravity in the International Space Station? Is it 9.8? Is it 7.8? Just one significant digit. What do you expect it to be? 0.01? Or is it exactly 0?
Yeah, maybe around 0.1.
0.1?
Maybe 1 magnitude less up there than here. Yeah.
1 order of magnitude? Can you guys do this calculation right now? Suppose I give you the number. You know how to calculate G, right? The G is this quantity, right? That's a mass of Earth. That's G, capital G.
So how far is the?
Yeah, how far is it? So it's about 300 kilometers.
Okay, so like 10 to 6, so it would be like 0.000.
No, 100 kilometers from the surface. And radius of Earth is 6,400 kilometers.
Oh, right.
Is that clear what I'm asking? So just for you guys to, so if you guys can calculate this for me, so G is roughly, it's not roughly, it is exactly radius r squared, right? G is 6 point, you see it's 6.7 into 10 raised to minus 11 of the unit of G. Newton meter squared over Oh, I meant the capital G. You're correct, meters per second squared for the small g. That's capital G. Mass of Earth is equal to 6.0 into 10 raised to 24 kg. It's just for some observation here. So radius, International Space Station is slightly above the surface of Earth, but it's not very much above. That's why it goes so fast, right? Have you guys seen International Space Station in the sky? Like you can actually, if you look up in the sky, almost once in every day, it crosses the sky, and it goes like almost like an aircraft. But it's the fastest moving object in the sky. So look up. I mean, it's kind of if you're interested in these kinds, it could be nice. So if you go to the internet and type in International Space Station, there is a website, and then you can register there, and it will inform you to send you a message that wherever you're first give your coordinates, and will tell you at this time for about a few hours before it will tell you that it's going to go from this direction to this direction. So you can. It takes about two to 3 minutes to cross the sky, so that gives you a speed, right? So pretty fast. Its angular speed is very fast. It's of course fast in the sense of any other astronomy, but since it is so close, it goes pretty quickly in the sky, and it's a bright object. You cannot see the features of the International Space Station, but it looks like an aircraft. But it goes faster than an aircraft. Goes pretty slow in the sky. It really goes quickly. That's kind of a nice thing, but so it's very close. So it's only 300 kilometers, 300 to 400 kilometers. The radius of Earth is 6,400 kilometers, plus 300 to 400, so if you want 350 or 300 kilometers. This should give you an idea of how much it is. If this 300 was not there, right, you know the answer. It is 9.8. So the question is, if you change the denominator by how much? 3 in 64, right? That's about what? I mean, so how much will it change? 5%. 5%, yeah, reasonable. So usually 10% that it changes. So the acceleration due to gravity on the inside of the International Space Station is about 8, let's say 8 meters per second squared, instead of 10 meters per second, 9.8 to 10. So pretty good, actually. I think so, if I remember that. I might be wrong. 3 and 64. But it's a square also. This is just from my view, because I've done this before. But the question I'm coming to is, okay, so this, suppose you can do this. How about that? This is a quiz. Okay, find out, calculate this just for fun. And now my question here is, so it is 8 meters per second squared. That's much, a lot more gravity than the moon, right? On the surface of the moon, it is just 1.5 meters per second squared. So anything you drop should drop faster than on moon. But you see movies of International Space Station where you're really floating around. Why? Is the question clear?
Because of
seriously, despite the gravity being about
8 meters per second squared, which is about 4 times larger than the moon. On moon, you don't float around, right? On moon, you fall down. When in International Space Station, you don't fall, like you're floating, really floating.
rotated.
yeah, big solid.
That gives you a hint of how will you get zero gravity. If you have achieved zero gravity, what do you do? It's not by getting away from the mass. There is an easier way of getting zero gravity. Sometimes you have heard about an aircraft which goes up in the air, and then for a few seconds you can experience zero gravity. Have you heard of this? How do they achieve that?
Yeah, like go up in my nose dive, so it's at the like when you're doing the curve, you're accelerating opposed to it. It's like you're like your momentum would be taking you up, but.
You're suggesting that acceleration is cancelled, so you're going to have an acceleration in the upward direction, exactly canceling that. I mean, that's a reasonable thing to think of, but that's not what they do. That's an easier, significantly easier. How about this? In this building, you can get this. Zero gravity. Or you experience it all the time.
Free fall.
Yeah, it's free fall. Oh, you just have to do free fall. Like when you jump out of the window or jump off the table, if you have to have a weighing scale with you, like sit on the weighing scale and jump off the table, how much is the weighing scale weigh? Just for that moment, it's zero because you're not pressing nothing. That's zero gravity. So you're falling, everything is falling with you. The International Space Station is actually falling. Like is that understand how is it falling? So when you fall on the table, it's visible. Yeah. So, when you jump off the table, this is a magnified view, you just fall that way. That's falling. So that's a small distance that you guys can see online. Just jump straight. But you don't have to jump straight down, right? You can also jump a little horizontal. Right? That's also jumping. Right? Free fall. That's also free fall. It's a missile. That's a continental missile. Free fall, still free fall. Right? And if you provide it with just sufficient speed, correct amount of speed, you keep free falling forever. That's International Space Station. That's a planet. Right? So pretty remarkable. It's just free fall. So it is 8 meters per second square, but everything is falling at 8 meters per second square, and it just happens to be at the right speed that it forever is falling.
Do they control the speed?
Yes, International Space Station actually doesn't have to be controlling. Now the point is that once you reach here, if you have just one amount of speed, right, that's a constant speed, you keep going in something. So once you reach that orbit, that's the equilibrium point. If you were to go faster, what will happen if you go faster? Let's say today, International Space Station puts a small rocket there. They have it. Decides to go a little faster. What will happen? They will go further out and that's it. And still it will be orbiting. Like stable thing is to orbit. And if it is, the only thing it will do is that it will go out or more. Like today, if a planet loses some energy, it will go closer or farther. Right? That's all that will do. Just it changes the radius. That's equilibrium point. And so once you reach that, it's just a matter of controlling a little bit, mostly to make it radius. That's how. Yeah. After that, it's free trip. You keep falling forever. Pretty nice. So that's the way you would generate zero value, but that's all digression. So how do you get zero electric field? Digression. But still, zero electric. That's slightly non-trivial.
Containing source.
Yes, exactly. So contain it inside a conductor. Right? A Faraday field, if there is lightning, where do you run? Inside your car, inside a new conductor, inside your conductor. And why don't you get signal inside an elevator? Not because it's a federal building, because the federal buildings are built of concrete or iron. Concrete has iron beams in it. Not because they were trying to save the signal, it's just that it's a safer building. That's all. Any government building typically has concrete and iron beams in it. So some signals are weaker because some signals do not penetrate. That I don't think they plan. But they can plan also. But I don't think they personally plan. But I don't. Okay, so zero gravity, constant. Zero gravity and constant gravity, zero electric field you put inside a conductor, and constant electric field, what do you do? How do you generate constant electric field?
Magnetic field.
No, simpler. Similarity with gravity, right? Like there is 1 over r squared, same as electric field, right? So how do you get uniform gravity? Infinite plane. How do you get uniform electric field? Infinitely charged plane, the capacitor. So inside a capacitor, the electric field is a constant, right? So, and we use that all the time. What happens to a charge when you drop it inside a capacitor, and how much time it takes, it's all the same kinematic equations that comes by. Okay, so all that with electric field, and the non-triviality is that the free fall concept is not there in electric field. Why is it not there? If there is one-to-one correspondence between gravity and electric force, Coulomb's law and Newton's law, a mass dropped on the surface of Earth, if it is freely falling, it experiences zero gravity. Why doesn't that happen when a charge is placed on, let's say, an infinite surface or on a sphere? What's the difference? No? So here, so is if you drop a mass here, is mass times acceleration is equal to g m over r squared. So, and what will be the same equation for Coulomb's law? Mass times acceleration is equal to, let me say, k q1 q2 over r squared. What's the difference you see? The mass cancels out here. So there is an inertial mass which is exactly the same as the mass that appears in the Newton's law. That's not there here. And that's the most important difference between gravity and any other force for that matter. So the left-hand side happens to have the mass in it. The dynamics or inertia is called is dependent on the force itself. Whatever is there inside the force is coming in there. And that's what is different about gravity. That's what makes gravity so difficult to understand, because its dynamic is decided by something that's invariant. So if you want to say that's inertia. But okay, all that's because I wanted to ask electric field, magnetic field, gravity in the electric field, constant and zero. So what about magnetic field? We are doing magnetic field. So before I ask uniform magnetic field, how do you get zero magnetic field? Huh? Don't move at anything. That's actually good. So you just stay static, right? With respect to the observer, you just stop and B cross B goes away. Another is a conductor. You can actually again use Faraday tapes for a conductor that works. And there is a third answer to this, which is kind of nice, but you guys have probably not seen the physics of that. But that is inside a superconductor. What is a superconductor?
It's if you freeze it or not.
Yeah,
Magnetic field.
exactly. Magnetic field goes to zero, but the simple idea of a superconductor is that if you have a current, it persists inside. It will never die away. In a perfect sense. It's not that it is negligible to our knowledge for many years. It is perfectly zero to many, many significant digits. And a consequence of that is, a non-trivial consequence of that is that the magnetic field inside a superconductor has to be exactly 0. It's called a London effect. So, zero magnetic field is a state set or be in a reference frame where V is equal to 0, nice, or be inside a conductor, or inside be inside a perfect conductor, or inside a superconductor, which also because of London effect is good. Now comes finally to the question of that interesting you. How do you get uniform magnetic field? Well, maybe it takes the simple way that statics. However, it might be possible to get it like that, but probably simpler since I'm doing statics. But it dies off. It's the magnetic field around a wire is very strong close by, and then it dies off.
You can have that same wire, but every so often you have like something that keeps the magnetic field up.
Yeah, but how do you do that? Yeah,
Yeah.
spiral, exactly. So you do that periodically, so that is what you do. That is spiral. It's a good part. But and what's that called? So solenoid. So it's the uniform magnetic field is achieved by a solenoid. That also counts. So let's consider a solenoid. Okay, and the solenoid is a so this is the idea. That's your solenoid, if that makes sense, right? And let's make it go to infinity. So, okay, but if you think of a cross section, it's easier. So I have few. So this is coming out of the board, and that's going into the board. Current coming out of the board, going into the board, and I keep it very close to each other. Coming out of the board, going into the board, coming out of the board, into the board, and so on. And so the magnetic field is uniform, we said. The claim is that the magnetic field is uniform. And let's say the radius here is A. First of all, what's the direction of the magnetic field?
Clockwise, around the left ways, clockwise. Or no, clockwise on goes right, and counterclockwise on goes left.
So this way, and this way. But that is the magnetic field here also, right? But that's not uniform because direction is changing, it's not uniform. So if it is really infinitely long and if it is really close by, it will actually be horizontal, or sorry, vertical. And since we say it is uniform, is it closer to the surface, or as you get closer to the surface? Like, will it be larger at the center and get deeper and deeper on the? It will be the same, uniform, right? So it has to be uniform. So let's say it's in the z direction. That's slightly non-trivial because as you get closer to the surface of the solenoid, you're not getting stronger, but that's like capacitor. If you go and touch the capacitor, it's the same voltage as you were a little distant away. So if this was z direction, that's z. Yeah. Okay. And I say it is constant. So what does it depend on? And it has to depend on the current, right? Each of this wire has a current I. So that is mu naught. For unit purposes, let me say mu naught over 4 pi. So it depends on I. Okay. What else does it depend on? Well, it's infinitely long. It should not depend on the length of the solenoid. Yeah, but what's the dimension of B? Magnetic field. Let's look into some one of this equation. Test equation is force is equal to QB cross B. If you want, that's one way to look at it. If you know the expression for any other magnetic field, we did the magnetic field due to a single wire, right? Infinite wire. What is the magnetic field due to an infinite wire? It is in the direction of phi hat, right? Last class we did this. It is equal to mu naught over 4 pi times 2 times I over not R, it is just R, but it is rho actually cylindrical part. It only depends on how far you are from the wire. It does not depend on the third Z problem. Rho is how far it is. So it's mu naught I over 2 pi rho. So you can cancel off, but this is the units, so I keep it. So it depends on a distance. Right. So dimensionally speaking, magnetic field is current over distance. And there's a constant there. So you already got that constant, so that's the distance. Right. So kind of tricky, you guys. So what should this be there? Okay. Because that's the only distance you see. So as I said, I'm tricking you guys. Actually, the magnetic field does not depend on the radius of the solid. Okay, so that's remarkable actually. Because anytime when something doesn't depend on it, that means you can actually squeeze it. If you squeeze it in, still it will happen. Okay, so that's something non-trivial. We'll use this feature later on. So okay, so that's so if you firstly, it does not depend on A. So what else does it depend on? Where is our line? Yeah, so it can't be infinite. Right. Yeah. So what's the expression for magnetic field in the solid? No, not line. It's got to be divided, right? Dimensionally, there has to be a line coming down. So what's the expression for the magnetic field in a solenoid? Remember? It is mu naught times I. I'll just give you that. It looks like this. So what is that?
The
Number of turns. Okay, but still very much diameter per unit length, right? Number of turns per unit length. So it is n is the total number of turns over the total length. But L is infinity, n is also infinity. So there's some constant. So the very large number of turns, very large length, but the number density is uniform. Some number of turns per unit length. So per centimeter. So that's n. So it is usually mu naught I n. So since I want to write it as 4 pi, so 4 pi. So without the units, that's what it is. Okay, so one interesting part of the solenoid is that it's independent of the radius of the solenoid. Remarkable. Okay, it's almost like the surface of the sphere where you don't see the dependence on the radius of the sphere. Now, okay, that's good, but what is the magnetic field outside the solenoid? So this is inside. What is the magnetic field outside? If you were to imagine,
It's either 0 or negative.
it is zero actually. Good point. Like because this actually goes away and comes back with it seeps out of the end of the solenoid, but it's really far away. Think of the North Pole and the South Pole. The solenoid is a good approximation of the North Pole, South Pole. So that's your magnetic field, right? And inside is like this. So inside part is here. The outside, as you get bigger and bigger, these will get farther and farther. So it doesn't come out like this. It actually spreads out. And if you make it to infinity, it will actually go out, but then it will go all the way to infinity. So it's pretty much zero. Again, not obvious. Right? So we can try to derive it, right? Either we can derive it using some basic principles, but we can actually use what do you call it? Ampere's law to derive that. So we would like to see that it is constant inside. In fact, we would like to get this expression out and to see that it will actually zero. So let's try to build this, at least part of this. Not full. In Ampere's law, whenever we try to do, we have to use a lot of symmetry. So we will argue that yes, it has to be the z direction. That's it. Based on symmetry, we will not require that because if it is really close by, each one of them adds up. So it has to be straight. That is going to be a symmetry argument. So the first thing we will say is that based on symmetry, we say that the magnetic field has to have the form z hat, but it could depend on, it's not very obvious that it should be uniform inside, right? Let's keep a radius dependence. So let's assume that there is radius dependence in there. There cannot be any phi dependence, that's symmetric. Right? The cylinder is symmetric with respect to angles, so that should not be there. It's an infinitely long solenoid, so it should not have any z dependence. Like wherever you are on z, it looks the same. Right? So no z dependence. So by symmetry, we can expect that it will be this, but apparently it is constant. No. Oh, okay. Yeah. So radius dependence is the only thing we have to look for, and that is zero outside. How does this and it is a independent of the radius of that. So those features we can get. So let's have our first thing. So we don't know what the magnetic field here. So let's have our loop. So remember, we need to first specify the loop for the Ampere. We can keep it anywhere we want. We will keep it inside the cylinder, and that's going to be our loop. Its radius, inside radius of this is a rectangular loop. So we're just having a radius of, so that this is the center, right? So the distance of the closer end of the rectangle is rho 1, and the outer is rho 2. The distance from the center of the solenoid, so the radial line. And let's say the height is h. Okay. So there are, so this is the loop you're talking about, and it is a surface. So we had a talk about the loop here. So that's rho 1, rho 2, and that's the height. Let's begin with the right-hand side of the Ampere's law. What is the current that is passing through this loop. There is a solenoid with a lot of current carrying wires, but this loop that I have picked, how much current is passing through that? It's zero. Right? So whatever I calculate for this left hand side, that has to be equal to zero. That's dl dotted with b, which is z hat, times b rho for this loop. This is the loop, is equal to zero. Because there is no current going through it. Let me split this into 4 pieces. 1, 2, 3, 4. What is this contribution? So let's say this is 1. In that place, dl is in the radial direction, right? So this is dl times rho hat, because it's in the radial direction, dotted with z hat times b of rho. So that's the first loop, right? And what is this equal to? Rho hat times dotted with z hat. Radial direction magnetic field is perpendicular. Right? That's 0. That's magnetic field is 0. So this is equal to 0. Plus rho 2, or the second integral, where dl is in the direction of z itself. So z hat dotted with z hat. But now I'm on the outer radius, so magnetic field is constant. That's just rho 2. Everywhere on this line, its radial length is constant. And third one is again 0. So dl rho hat dotted with v hat times v rho plus the fourth piece dl, but now it is in this minus z hat direction. It's minus z hat dotted with z hat times magnetic field now is rho 1. It is all equal to 0. The right hand side that is 0 is this. No. So that's 0. That's 0. That is 0. Here z hat dotted with z hat is 1. B of rho 2 is constant everywhere. That can come out. What is remaining is the length integral, which is just height h. So we get B of rho 1 times height h minus of height of h times magnetic field of rho 2 is equal to 0. H cancels out, and I learned that magnetic field at any radius rho 1, because this loop was pretty much arbitrary, is equal to another radius. So this means that it's constant everywhere, uniform everywhere, uniform inside. You can repeat the same thing for another loop outside, because all the arguments will go through. Again, we will assume that whatever is the magnetic field in there, it can only, we'll say that it has to be in the z hat direction. It could be minus z hat also, but whatever it is uniform. Right? That's the first thing we can conclude. So whatever same argument will go through that, and it is going to be uniform. And then we have to argue somehow that, okay, how do we get this expression? And that's the fact that it is 0. So still remaining things, but we'll come back to it.
Why does it have to be uniform outside the solenoid?
Oh, we have to conclude that. Same argument, right? First we argue this, right? It is the hat and B of rho. It cannot depend on the angle.
So what if it does? Because I can see how on the inside you have, contributing factors from both sides, but I think that the case would be different outside the solenoid.
No, if it was a cylinder, right, infinitely long cylinder, whatever is here has to be there, right? A cylinder has no property, right? Angular property. Is that clear? So it's angle independent. Can you accept that? Then I say it cannot have any z dependence because whether you're here or here, because it's infinite, it doesn't matter. So it cannot have z dependence. It's symmetric argument. Direction it is not very obvious. You can argue that okay, maybe there's a direction here, but for that you have to go into the divergence of field coming in. So direction I have cheated. I'm not trying to convince you too much. That because I need another equation. But it can be argued that we have direction. So once you have this built up, argument goes through because the same loop and it's just outside. Again, this is 0 on the right. So whatever it is constant outside. Does that make sense? It's pretty generic argument we are making that just based on symmetry. That's the power of Ampere's law. But usually, symmetry also has this feature that you're afraid that, oh, did I miss something? Right? So there's an uncanny feeling.
So now I'm worried about like the currents that we accept, right? So if the current's moving in the coil, does that still count for Ampere's law? Is that still a static current? Is the divergence of that current truly 0?
Oh, it is. It should be 0. Yes. And how do you know that it is 0? Yes. So remember that del dot j, right? How do you make sure that del dot j is equal to 0? There shouldn't be j coming out of it. So wherever it originated has to end, usually it has to be loop. Right? But in this case, it is originating at infinity and ending at infinity. So in that sense, if you're not satisfied about that, what will happen is so that is the curl effect, right? So somehow it is going to see end, right? But this effect will be negative. There's a small bend there, but its length is very large, right? At this point, it will be very close to zero. If you don't like that argument, you have to go through that. That's harder calculation because of symmetry fails, but it can be done in control. It's exactly like the capacitor. Little seems thin, but we're okay. Like our gravity here, is it 9.8? How sure? It's almost too significant because it's constant. It is 9.78 and 76 number, or 9.8, 2 6 digits. It's the same everywhere on the circuit. So, yeah, so we'll come back and go over it. Meanwhile, did I give you a quiz? Right? It did. Yeah, how about this? Add to that question solenoid. Look up the derivation of Ampere's law derivation of solenoid expression. You should have seen this in your 205, right? No, probably, yeah. But then that you go so quickly. It's the same thing here, right? So many things I could do. The next speaker can come. So you should have seen this in potential. Many things. Okay, that's all. I should stop. Thank you.
See you.
That is great. No, you love it. Yeah.
I feel like so if I were to look at it, not having seen that it was supposed to be there outside, I would say that it would be radially dependent outside in straight lines.
Radially dependent outside.
And
Oh,
straight lines
dependent.
down, and it would get weaker.
But how about this argument?
I'm not satisfied with, because you're assuming that the V field is only in the Z hat direction, but I don't think that that's the case outside, because if the wire's coming up, there should be current on outside at each point.
Yeah, make it squeezes. It's curling out that squeezes. Oh, you're talking about this curve or this curve?
Both, yeah. Well,
Yeah.
I'm talking about the individual curves.
This make it close, make it thinner. There's so many people. Make it closer and closer. So that curve becomes, yeah, it does. So, but then we have good approximation to spec up. Right. Like I'm saying, if you were to, like, how would you do a flat circle? If you have one earth here, two earth here, three earth here. Right? If you make small, make this radius smaller, and then you put a lot of them, yeah, gravity will get changed here, but then this will flatten out if it's in that limit. And for that, yeah, and
Yes, exactly, it will, I agree. I agree that it'll go to a straight line. I agree, but I don't think that, I don't see how it goes to zero. Right?
oh, yeah, zero is not okay. Yeah, I'm just saying it's constant. I did not say it's zero. I would say it's constant.
I don't know that I'm convinced that it's constant.
Yeah, but then you're going through the argument. Only thing here that catch is that we just may not be satisfying because you don't have so much experience. Is that are you sure this divergence of J is zero? That has to be like you're basically say that it starts from infinity and goes in. It's the same thing that wire. Well, this the divergence is not zero. Right? If this is a finite wire, this is not zero. So this the formula works only if you go very far away. Like when you say that this is a loop like this, and especially the magnetic the vector potential after a certain length, this is length L, this works only for L. If you go beyond that, things go off because you're talking about infinite. So you have to be very close. But if you're very close, that's pretty good approximation. It's not really it's often we think was the infinite bad approximation. Make it small. So this length is very small compared to the so the third significant integer. That's the way of infinity. Right? So in that sense, okay, so you are making this, if you want, you're making this approximation, but this approximation is okay within three significant digits. You get very close. If this is very long, and if I come very close here, then it is constant. That's all I'm saying. Whether it's zero or not, how is it going to zero? I'll let you think.
But now, so I feel like this disagrees with if you were just looking at Maxwell equations alone.
Yeah, which one will it disagree?
That the magnetic field is generated around the current because it's a change in electric field generates magnetic field.
But there is no change in electric field.
Through a current though, but like if you have any current.
Oh, you were again about this. Remember that, see, that's what first class comes in. Remember that this, right? I think you bothered about this, right? So that way, if you say no current, then a current carrying wire should create electric field. Right? Not always. Current carrying wire will not always create an electric field. It creates a magnetic field. So you have to have, so if it is static, this is gone. Charges are not moving. Then you say, how do you get a current without charges not moving, right? So you have to have a current that satisfies this. That means it is steady. Or more than steady, it will be loops.
So experimentally, the magnetic field outside of solenoid is zero.
Is it?
Then I think that there's something wrong with that equation itself.
This one.
Because you have to assume that del dot J is zero only at infinity it works. But experimentally it works and you don't have an infinite solenoid.
Yeah, but I think that's an approximation, right? That's the same thing as when you say Earth, right? Is it constant? No, right? The same thing. You have a finite wire, but if you go close enough, let's say if you're 1 centimeter and this is 10 centimeters, right? So within 10% accuracy, it will be zero. If you measure only 1 stick digit, it will be zero. Right? So infinite lengths are not that bad. But convince yourself. Yeah.
I think that I think I'm holding too much value to like the concept of if I like think about a current flowing through a wire, I'm just thinking radiomagnetic field around it. But yeah, I don't know.
Radial magnetic field current going through a wire. That's correct. Radial magnetic
If I throw that on the solenoid, then you're going to get a radially dying.
radially dying. But now what is happening here is that this one is all acts up this way. But this one is, I think the point is here. This has to come out of here, then this kind of disperses out. Like what? Okay,
But see, I don't
Yeah.
know why that is either. Why does it not just come straight down? Why would it not be as close to the first one as possible? Because
good
the
question. Okay.
magnetic field is still as close, and then the next one is just as close. So why would that?
Because of the radial, that's equivalent to saying, yeah, 2 pi times rho, right? You have to capture all. And it's like saying that, yeah, think of this. Why is this? This is taller, right? It has to be the same everywhere. So in that sense,
It's was.
yeah, there has to be, once you go outside, you have to lose it. Because if it is constant, it will be constant everywhere. Like equally distance everywhere.
But
And
that's
then it
great.
will go all the way to infinity. Right?
But that's very singular. So now we have infinitely many.
Yeah, but this is magnetic field. Remember, magnetic field is a loop. It's not charged, it is a plane. Right? So we have to conserve the same similar situation. So here is the volume, right? I do a flux. But in a magnetic field, it is circumference. It's plane. So whatever comes in here will be the same thing. But still, there is a catch in yet in your right, which is probably what is bothering you. Like, why not go like this? Right? So how will I set this to? I want to set this to be constant. Maybe that's the key to this. Is that how will I set this to 0 now? Then I will require that at infinity you cannot have magnetic field. Right? So if you set 1 point to be 0 because it's constant, it's 0, 0.
See, but if it was radially dying, it would be 0 to infinity too.
Yeah, but then this has to be constant.
No, I don't like this argument. Okay. I'll think.
Yeah,
some more
think about it. Yes, there's fine arguments here, but this is the only thing I think you probably may not be comfortable with, or comfortable with the fluency in that.
Yeah.
But rest of it is to a part, like you will be able to.
I'm never.
You'll accept it.
I'm not a fan of symmetry arguments typically because it require infinity. Well, for this.
But they're very powerful and usually.
But maybe they make it too simple because you're looking for the simple solution.
But okay, how about? Yeah, let me see. But I don't think you can escape the symmetry argument will always have.
But you see what I'm saying, though, right? Like I can see uniform magnetic field inside easily justifiable because you're stronger here and you're weaker over here. They have the same, and then in the middle they're both doing the same. I can see that. But over here they should all, I don't know. I see like I don't understand how it extends.
Think of this. I think that is the point. Or think of it here. B dot dl, right? Has to be that this is the same. Like think of Gauss's law. This is the same. Volume wise you go out, volume increases. Right? Volume increases, magnetic field has to decrease exactly the same. This is constant. Right? This is constant. The circumference, if it increases, this has to go down the same so that we cancel. I think that's a correct argument. You see what I'm saying? These two have to be the same.
But doesn't that
Give you a
mean
concept.
okay, so at any any ring around any of these, your charge stays the same, and then the magnetic field has to die radially.
That's
right?
correct.
For all of them. And there's nothing else out here to affect that. So why does it go to this? I see what intended like the radius. I see your argument, but I don't know why that's the case. Really. Like why couldn't it not? This still satisfies. If you draw a circle, small circle here, and then larger circle. Yes, I agree that it has to be bigger, larger circle. But why can you not have it?
But if okay,
Oh,
I
because you're
remember
saying
this
that
also.
infinity is 0, so
Yeah.
it has to be.
And it has to be constant. So it is like saying
see,
it
they're
is like-
constant everywhere. That's why that.
Yeah. So because then you can bring this out kind of. And if it's constant, how can you get the normal?
But yeah,
And the constant argument again is a third argument, right? So there's a loop here. Again, use Ampere's law.
which maybe Ampere's law is not valid. Because it might not.
Check it out.
That's
Find out.
what I need to-
Yeah.
Because
But
that's the only argument. I can-
this is the only way you can catch it, but this is okay. And that, I mean, that's just inexperience. Like, I'm not forcing you. Yeah.
Ampere's law here is what makes, that's why I think I like it.
And usually, I mean, so you go and look at it, like you won't see all this detailed argument. Like typically, you only see one loop here, and rest everything is kind of swept under the rug. But one can go through. But yeah, question, think about it.
Yeah, I think that's all it is. Like my only argument would be that Ampere's law is valid because that's the only thing. Like,
And
that would
actually,
be the
I
only thing.
think honestly speaking, there are, I have seen articles written where you say wrong, mostly for the single value, that's how we see. Oh, it's finite and doesn't work through, but that's all again because you have to bring in this feature. So static stands, so these are called steady terms. Like first of all, it should be a loop, it should end somewhere. You cannot just magically, like here it seems that this is, it has to end, and you can make it end at infinity, say like J. So that's an uncomfortable thing, you can question it, but then usually, how do you convince yourself, okay, forget Ampere's law, let's do it from the scratch. It's a lot more work, right? Lots of work, especially this one is reasonable. It can be done at this level, and you do the same. Then contract.
And you're assuming here that there's no sources, right? Because that would be the other term that.
But this one is no, there is no source, right? If this comes from Max,
You're just saying you're in the
so here statics is another. So and how can you get statics, or how do you get current without charge moving? It's steady.
Yeah. Assume that everyone is not in this. But can't.
Steady partial. It's not total.
Maybe it doesn't tell the whole story.
Yeah, you should question it. Yeah, I agree. The thing was, yeah.